Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss the module Examples of the change in the properties at nanoscale and the introduction to Mesoscopic physics from the paper Physics at Nanoscale. So, students, the learning objectives of this module are: first, the examples of the change in the properties at nanoscale will be discussed. Second, quantum coherence, quantum transport and weak localizations, their concepts will be discussed. Lastly, we will also discuss the concept of dephasing by electron-electron interaction and Thouless energy. So, students, let us start with a basic introduction about the module. At nanoscale, various properties changes due to the previously discussed effects, quantum confinement and change in electrical properties and optical properties for the nanomaterials will be discussed. Now, next we will also introduce about the mesoscopic systems. A mesoscopic system is the one whose size is in between the microscopic and macroscopic systems. It could be much larger than a few atoms or molecules or nanoparticles, but it is small enough that the degrees of freedom are to be regarded as quantum mechanical. A mesoscopic system has a size that is larger than microscopic length scale A. For example, the Bohr radius or de Broglie wavelength, yet typically smaller than a length scale known as phase coherence length L phi, which is the characteristic length beyond which the wave function represents the system. It loses the phase coherence. L phi generally depends on the dimension, the microscopic details and the temperature of the system. Therefore, a mesoscopic system in which quantum mechanics is fully manifested is the one that is larger than microscopic or macroscopic system. So now students, let us discuss the examples of the change in the properties at nanoscale. First, we'll discuss the quantum confinement and electrical properties. The electrical properties of a material depends on its electronic configuration. Based on the energy gap between the valence and the conduction bands, the materials can be classified as conductors, semiconductors, and insulators, and their electronic band structure at 0 Kelvin is shown in this figure. The electrons associated with conductors and semiconductors are either tightly bound to the nucleus of the atoms or are free to roam about in the bulk of the material. It is these free electrons that can be confined by means of the effect called as quantum confinement. In the bulk materials with larger number of atoms, the energy levels are so closely spaced that they resemble bands. The spacing between the levels is being inversely proportional to the number of atoms. Having very few atoms in the material, however, causes the energy states to spread out and widens the band gap. So, the expression for energy difference shows that as the size of the sample is reduced, the spacing between the energy levels increases and the discreteness of these levels becomes more pronounced. It is possible to create the islands of conductor and semiconductor structures in the interior of insulators to confine the electrons. So students, if we are reducing the volume of three-dimensional structures, we have to reduce the sample to a size in which at least of the dimensions falls to less than 100 nanometers. Now, constraining the electrons inside a region of minimal width creates a quantum well which can be realized and fabricated from alternating layers of different semiconductors or by deposition of very thin metal films. By further constraining the depth of the electrons domain, a quantum wire can be created from quantum well. Now, when all the three dimensions are minimized or when quantum wires are chopped into small pieces, we get quantum dot. The dot can be a particle located inside a larger structure or on its surface. In metals, the particles with diameters ranging from 1 to 10 nanometers can behave as the quantum dot, but in the case of semiconducting nanoparticles, quantum confinement is seen for sizes up to few hundred nanometers. The conducting nature of the metals can be transformed to insulators as the size is reduced because of the increase in the spacing between the energy levels. The fact that metals have overlapping valence and conduction bands changes at the smaller dimensions, and it is seen that the metals exhibit a band gap and are converted into semiconductors or insulators if the band gap at a particular temperature exceeds the thermal energy available to the electrons at that temperature. So carbon nanotubes, for example, can behave as the conductors or semiconductors depending on their nanostructure. So students, let us now discuss what changes occurs in the optical properties of nanomaterials. In general, light is incident on a material, is transmitted, or it can be absorbed, or it will be reflected. The color of the material is determined by the wavelengths of the light reflected by it. A material, it absorbs light of certain wavelengths depending on its energy levels. It is a molecular phenomenon which depends on the chemical constituents and the structure of the substance, and also on the electronic, rotational and vibrational transitions. An observer will not see the colors whose wavelengths have been absorbed, and will not only see the colors associated with the reflected light. For example, leaves appear green because the chlorophyll, which is the pigment, it absorbs blue and the red colors of the spectrum and reflecting only the green color. Another phenomenon that is important in determining the color or the transparency of a material is the scattering. It is the phenomenon that occurs when light is incident on a structure with the dimensions comparable to its wavelength. It is a physical process which is different from the phenomena discussed earlier, and it depends on the size of the sample. And in the case of suspension, it also depends on the index of refraction of the cluster and the index of refraction of the suspension medium. The wavelength of the incoming light and the outgoing light, they are the same. It can be shown that the maximum scattering occurs for the wavelengths twice as large as the cluster size. Thus, for the structures with sizes in the nanoscale, the scattering of light plays an important role in determining the color and the transparency. Nanomaterials in general, they can have varied optical properties as a result of the way the light is either absorbed or scattered from a nanostructure. For example, the color of the butterfly wings is the result of the constructive interference of light wavelengths as they interact with the photonic crystals, which is a nanomaterial embedded on the wings of the butterfly. So now students, let us discuss the nanophysics and mesoscopic physics. Nano means the length scale is around 1 to 10 nanometers. Nanophysics is widely used expression for physics on the small atomistic length scale. Mesoscopic physics, that is, between the atomic scale and macroscopic scale. But the two types, they have the common ground, that is, the wave nature of electrons, it becomes important. And the quantum scattering theory of electron transport. Current in a conductor, or we can say the quantum transport. Now students, let us try to understand the different length scales defining the motion of electrons through a conductor. The most obvious is the geometric size of the conductor. The size may be different for 3 dimensions x, y and z, and we can assume a characteristic dimension length L whose comparison with one of the other length scales determines the behavior of the system. The next length scale comes from the fact that in mesoscopic system, the electron is considered to behave as a wave that depends on the energy, has a characteristic wavelength associated with it. For electron transport, nearly always only those electrons becomes important whose energy is close to the Fermi energy. Thus, the Fermi wavelength is a relevant length scale in a variety of quantum effects, in particular those depending on the wave interference. So, the non-equilibrium statistical mechanics corresponds to the electron transport, basically the Boltzmann transport equation, that is I is equal to Q A N V. And according to the quantum mechanics and statistical mechanics, it follows the Fermi-Dirac statistics. Now, let us summarize the different length scales. A mesoscopic system has a size L, that is small l, that is larger than a microscopic length scale A, yet typically smaller than a length scale known as the phase coherence length L phi. So as shown in this figure, the total length, that is capital L, and L phi is the phase coherence length. That is capital L is the size of the conductor, that is a geometrical dimension, and L phi is the phase coherence length, that is the distance an electron travels before suffering a phase change of 2 pi. LE is the elastic scattering length. That means it's a mean free path between elastic scattering events. Now here Lin is the inelastic scattering length, that is the distance an electron travels before losing an energy kT. So now the conditions on the length scale which categorizes the macroscopic conductor and mesoscopic conductor are: for macroscopic conductor, we have Le to be very much less than L phi, less than equal to Ln, very much less than capital L. For mesoscopic conductor, Le is very much less than capital L, very much less than L phi, and less than equal to Ln. So now let us discuss these length scales in 1D, 2D and 3 dimension. The electrons in a mesoscopic conductor, that is a conductor with length smaller than L phi moves as a wave, not as a particle. Similar to an electromagnetic wave propagating inside a waveguide, and wave-like nature of the electron is mesoscopic conductors. That leads to many unusual physical properties which are revealed only after 1988. Perhaps the most profound is the origin of the resistance of smaller system. Resistance is generally caused by inelastic scattering of the electrons with disorder, other electrons, and with phonons. So now, in a mesoscopic conductor, however, an electron typically travels the entire length of the system without undergoing phase-breaking inelastic collisions. Apparently, this seems that there would be no resistance at all of a conductor whose length is less than L phi. However, to determine experimentally the actual resistance, one has to attach the leads with R ought to be the macroscopic contact pads. Now, as you can see over here, that in one dimension we have the conductance to be equal to sigma by capital L, and for the mesoscopic conductors we have capital L to be less than L phi, and the conductance is equal to sigma by L. So when L tends to 0, G tends to infinity. Now if we'll go to two dimension where the two length scales will come into picture, that is the width and the length. Width is W, length is L. We have G is equal to sigma W by L. Now we'll switch over to three dimension where we have three scales, that is L, W, and this width is same as the depth. So G is equal to sigma W square by L. Now in three dimension it becomes the macroscopic, that is L is greater than L phi. So in this scenario, the Rolf Lander in 1957 proposed that the magnitude of the resistance as shown in this 3D is determined exclusively by the contact pads in a mesoscopic conductor. That is, if we connect the voltage and we can experimentally measure the resistance, that is V by I. The Lander formula shows that the resistance of a mesoscopic conductor is inversely related to the quantum mechanical probability that can propagate through the system without scattering inelastically. So this formula is unusually successful in determining the resistance of a mesoscopic conductor. Weak localization. Weak localization is another important consequence of the phase coherent nature of electron transport in a mesoscopic system. To understand the weak localization it is first necessary to understand the Anderson localization, which is also known as the strong localization, is the absence of diffusion of waves in a disordered medium. This means that the eigenstates of an electron in a disordered environment, it becomes spatially localized around the impurities, causing the system to behave as an insulator instead of a conductor. Whereas the weak localization is a very different process that also increases the resistance of a disordered conductor and is resulted due to quantum interference effect that occurs in the systems with time reversal symmetry. So the probability P for an electron to propagate from the point tau to tau point, the tau prime, is the sum of the quantum amplitudes. All or the AI for the electron to take all the possible paths, that is the path is I, and then calculate the modulus squared, that is P is equal to summation over I, the modulus square. This can be viewed as the generalization of the double slit interference with the infinite number of slits. The cross terms in the expression, they are responsible for interference. So, in a normal conductor, when different paths tau to tau prime were considered, the randomness due to inelastic scattering, quantum interference effects are washed out. However, in a mesoscopic conductor, there is a special class of paths, closed paths with tau is equal to tau prime, where interference effects can be important. So in the systems with time reversal symmetry, that is in the absence of any magnetic field, there will always be the pair of closed paths and their time reversed counterparts in the above summation that have the same amplitude, resulting the probability to go from tau to tau prime is enhanced by quantum interference effects between different scatterers, and this leads to an increase in resistance which can be measured experimentally at low temperature. So students, let us now discuss the dephasing by electron-electron interaction. As explained above, the effects of weak localization is significant when the electron motion is sufficiently phase coherent. This fact can be exploited to measure the phase coherence length L phi or phase coherence time tau phi, the characteristic time beyond which the electron becomes decoherent. So L phi and tau phi, they are simply related to each other. The increase in resistance due to weak localization depends on the number of closed paths that contribute to the summation in P, that is equal to summation over I of AI, the modulus the whole square. For a closed path in a length of the sample, so that L is less than small l phi. Otherwise, if capital L is greater than l phi, the electron would not have the phase coherence necessary to exhibit the interference. In case of L, the capital L, less than l phi, it is possible to turn on and off the weak localization effect by applying a magnetic field and can be used to determine the value of L phi or tau phi. Now, at low temperatures, electron-electron scattering is responsible for phase breaking, and the fluctuating electric field produced by other electrons scrambles the phase of the electron after some time, that is tau phi. It is predicted that the dephasing rate vanishes at low temperature as tau phi minus 1 to the power minus 1 is proportional to t to the power beta, where beta is a positive exponent. But recently it has been shown experimentally that there is a saturation of tau phi to the power minus 1 in the t tends to 0 limit. So now this issue requires further investigation and is currently a problem of great interest. Thoughtless energy. The extensive research on mesoscopic physics in different nanosystems has led to a profound new discoveries and new insight into the quantum systems. In particular, several new aspects of quantum transport in mesoscopic systems have been revealed. In 1970s, there was a scientist, David Thoughtless, which showed that any quantum system possesses an important fundamental energy scale called as Thoughtless energy, that is ET, which is essentially a measure of how sensitive the eigenstates in a quantum system due to change in boundary conditions. Specifically, ET is defined as the energy change of a state at the Fermi energy when boundary conditions changes from periodic to antiperiodic. So ET would be 0 in an insulator with localized eigenstates, because if the wave functions do not extend to the boundaries, their energies will be independent of boundary conditions. So Thoughtless shows that the dimensionless ratio, that is small g, is equal to ET by delta E, where ET is the Thoughtless energy and delta E is the energy level spacing at the Fermi energy, can be used to determine whether the system is a conductor, that is when G is greater than 1, or an insulator when G is less than 1. So students, let us summarize what we have learned in this module. First, the dimensions of the material for quantum confinement is reached when the size of the material becomes comparable to the wavelength of the electron. The conducting nature of the metals, they can be transformed to insulators as the size is reduced because of the increase in the spacing between the energy levels. Secondly, the nanomaterials in general, they have varied optical properties as a result of the way the light is either absorbed or scattered from nanostructures. Next, the electrons in a mesoscopic conductor, that is a conductor with a length smaller than L phi, moves as a wave, not as a particle. Lastly, we also discussed about the mesoscopic conductor, where the resistance is caused by the combination of elastic scattering of electron waves from disorder and coupling with the microscopic levels. Weak localization is another important consequence of the phase coherent nature of electron transport in a mesoscopic system. Next, at low temperatures, the electron-electron scattering is responsible for the phase breaking, and the fluctuating electric field produced by the other electrons scrambles the phase of the electron after some time, that is tau phi. Lastly, students, we also discussed that any quantum system possesses an important fundamental energy scale called as Thouless energy, which is essentially the measure of how sensitive the eigenstate in a quantum system due to the change in the boundary conditions. Thank you.